right? For the definition of the antiderivative is a function f is called as an antiderivative of a function simple f if the following condition is satisfied. So what that means is f dash x should be equal to fx, right? And so this is now written as for all x in the domain of I mean, you just don't need to remember these things, right? So what is important for us is how to apply this. So what this basically tells is if you have a function capital F, it will become an antiderivative if this condition is satisfied. So what that means is if you differentiate the antiderivative, you should get this function simple F. Now, for example, let's assume that your function simple F function is equal to 2x, right? Now, from the power rule of the differentiation, we know that if I define the capital Fx function as fx squared, and if I differentiate this, that means f dash x, you will get the answer equal to 2 times x. Right? So this is the answer, which is basically equal to this function right here, right? So this is basically an example of the definition. So we can tell that this function fx, which is equal to x squared, is an antiderivative of the function 2x, right? Now the question is there any other functions that will give you the same answer, which is equal to 2x, right? Now think about this function right here, x squared plus 5. And if you differentiate this one, you will still get 2x because the plus 5 is a constant. The differentiation of a constant is equal to 0. So you will still get the answer as 2x, which means if you add any constant to this function, let's say a constant c, and differentiate it, you will still get the answer as 2x, right? Now, so what that means is any function fx that is equal to x squared plus c, and this c is a constant, any type of constant, we can call this as an antiderivative, is an antiderivative of the function f, right? Because when you differentiate f dash x, you will get fx. Now the f dash x is what? 2x. And fx is what we defined as 2x, right? So this is how we define an antiderivative, right? Now, the only important thing here is basically is that it is not only x squared is when you differentiate x squared you will get 2x, but apart from that, even if you add a constant like this to the x squared and do the differentiation, still you will get the same answer, which is 2x. So what that means is for this function small f has a family of functions that can become antiderivative, because when you put any constant right here, like 1, 2, 3, or 3, 4, 5, like that, all of those functions will become antiderivatives of this small function f, right? The small means a simple f function. Now, by keeping this in mind, can you try to find the antiderivative of these functions? So this will also check your knowledge about the differentiation as well, right? Now let's find antiderivatives of each of the following functions. So let's say the first one is function called fx equal 3x squared. Now you need to find the antiderivative of fx. Right? So that means you have to find a function called fx, and when you differentiate that particular function, you should get this answer. Now what should be the function fx equal to? So there should be a function, let me have a blank box here. There should be a function when you differentiate that particular function, you should get the answer as 3x squared, which should be equal to fx once again. Right? So this is what you should have. Now you have to find the function that you should put inside this box. When you take that function and differentiate it, you will get the answer as 3x squared. Right? Now what is that function? Now you have to do think about the differentiation in the reverse way to figure out this function. Now the answer for this question is, let me do this with you, should be x to the power 3, right? Now how did I write that is, when I now think about differentiating this function, take f dash x, and the answer will be 3x squared, because this x will come to the front side and then you have to reduce the power by 1. That is the power rule that we learned from in the differentiation lesson, right? So that's how you basically find an antiderivative, right? If I get a second example, now if you remember the equations that you have used for the differentiation, this will be easier for you, right? So these are connected, right? Yes, one of you have pointed out this should be x to the power 3 plus c. That is exactly correct. You should write x to the power 3 plus c, right? Because when you write x to the power 3, then you get 3x squared, but you can get the same answer by x to the power 3 plus c as well, right? So that is exactly correct. Thank you for that. Now, how about this function? Fx equal 1 over x. Now, what will be the function fx or the antiderivative of this function. Can anybody tell me the antiderivative of this function, or just mention it here? Right, maybe you don't remember the equations. Now, if you remember the differentiation, yes, this should be ln x. So this should be ln x plus c, because if you remember, when y equal ln x, once you differentiate it, the answer was 1 over x, right? So basically we are looking at the reverse of this. So you are given 1 over x, you are asking what is the antiderivative, which should be ln x and then plus c. So that constant counts, because every constant will become 0 once you differentiate. Now what happens if I write fx equal, let's say, sin x? What will be the antiderivative function for this one? For the fx equal sin x. Anybody have any idea about it?
Minus cos x.
Yeah, exactly right. That should be minus cos 6. So if I write, let's say, the easier way to think about this, if you are confused about what I am doing, let me write first fx equal minus cos 6, right? And then differentiate this function and see whether you get this answer. So that's it, right? So your answer was minus cos 6. In fact, you need to add that constant. So you add c and then differentiate this function and see whether you get sin x. Now what you know is, when you differentiate cos 6, you will get the answer as minus sin x, right? And then you have a minus sign here, and plus, once you differentiate the constant, you will get 0. So minus times minus plus, so the answer will be sin x, which is what you have here. So your answer should be exactly correct, right? So that's what you have to do to find an antiderivative, right? So I can continue in this way for a number of examples by reversing the differentiation formulas that we have used, right? And now let's see how we are moving into integrations by looking at these antiderivatives, right? So integration is basically just applying a formal notation for what we have done up to now about antiderivatives, right? That is, if you remember that so let me write it here just to make it clear. So that's just to get you an idea about the integrations. And if you have a function, let me say for a given function, if the differentiation of this function, we normally use to denote it either f dash x or dfx, right? f dash x or df over dx denotes the derivative of f. Now this is what we know, right? So we have been doing this in differentiations. Now what we are doing is we are going to introduce a notation for antiderivatives. Of the function f. Now what we know is fx plus c is the antiderivative of f, right? Fx plus c is the antiderivative of this simple f function, right? X plus c is the antiderivative of simple f function. Now, this is what we did, right? In these examples, that's what we did, and there is the definition as well, right? So what we are doing is just introduce a notation for this one. Now, to represent that fx plus c is the antiderivative of this function f, we write it mathematically using this symbol right here. The symbol is something like this, right? So if you haven't used it, just note that how I write the symbol. And then you write this function fx, and then there is the notation dx, and that is how we represent antiderivative, right, of f. So antiderivative of this function is equal to the function fx plus c, right? This is how you just convert everything that we did here at the beginning to the integration symbols, right? And this symbol right here is actually called as the integral sign. And this is what you may have seen in your notes when there is something for the integrations in physics, you regularly use this sign. And there are some names. This particular section right here. So let me rewrite it. The integration sign fx dx, and this is called as the indefinite integral, right? So this is just an idea, and if you look at the book, there is a definition for this as well. And so let me just write the definition, which basically tells you the same thing, right? Well, let me combine what the definition tells with this function right here. So normally fx, this function fx is called the integrand. Once again, you don't need to remember these things, but just get used to those words. Integrand, and this x right here, here and here, that is the variable. So that x we normally call as the variable of integration, right? Remember that when you differentiate with respect to x, we used to tell that differentiate with respect to x. So that is the variable. Now here we used to tell this as x here as the variable of integration. Now as you see, the integration is actually, we can tell that as act of finding the antiderivative of a function x, sorry, function f, right? So if I just write it here, act of finding the antiderivative of a function f. So this is equal to integrating f. So what this means is actually when in future I will just mention that to integrate the function f. So what that means is you are just trying to find the antiderivative of this function, right? So that's all. That's actually, that is the only thing that we do under integration lesson, right? The problem is when you try to find these antiderivatives, when the function gets complex, it is not easy to find these antiderivatives, right? Because of that, there are different techniques that mathematicians use to find these antiderivatives. Now, these functions are easy that I have I did with you these three examples. These are straightforward because 1 over x, we know that antiderivative is ln x, because once you differentiate ln x, you get 1 over x. Same thing for 3x squared and for the sin x. So you gave these answers, right? Those are straightforward now. But when you go for the next step, when you have these little complex functions, you can't directly use these results of the differentiations to find the integrations, right? When the function becomes complex. So when you go through some examples, you will see it, right? And remember this name also, we call this as indefinite integral, right? Because we have not set something called limits. We will see it in some of these later problems. So in details about this, when you go with the details to the next sections. And the next thing I would like to talk is, let me write the very first example here using the same, this example right here that we talk, if x equal x squared. Let me write this now using, so what we saw here is the antiderivative of x squared has become 2x, right? The simple f function is 2x, right? So if you look at, if you use the symbols, now we know we can write that integration of 2x. So this is the function f, right? Right, so this is the function f. And the answer for this one is x squared plus c, and this is what we called as fx, right? So basically, in brief, this is just like do the reverse thing of the differentiation, right? So you are given a function, you need to find the answer is which function once you differentiate will give you back 2x, right? So basically when you differentiate x squared plus c, it will give you 2x. So which in other words, the integration of the 2x is equal to x squared, right? So this is going in the reverse way compared to the differentiation, right? Now, the difference is that when you do a differentiation, you will just get one function. But when you do an integration for the 2x, you will get x squared and then plus c. So which means there is another constant. That constant can get different types of values, right? Now, if you go to the book and look at, so let me write this figure number here. You can give very different values here and see how that works. This differentiated function, right? Now, as an example, if I plot this function x squared, normally if c is 0, the x squared will be something like this, right? But if this is 1, then this curve will be x squared plus 1. This is equals to x squared. And if this goes to 2, this will be x squared plus 2. The similar way, if you go to minus, if this goes to minus 1, this will be x squared minus 1. So you can see that if this is minus 2, this will be x squared minus 2. Right? Like that, you can have number of functions as answers depending on the value of the c. But if you differentiate, you will only have one answer, right? So that's the difference. Now, remember that now I will directly go and talk with you about some of these integration techniques. Now, remember that for the differentiation, we had set of rules at the end, right? We know that when you differentiate sin x, the answer will be cosine. So when you differentiate x squared, the answer will be 2x, according to the power law that we learned. And if you differentiate ln x, the answer will be 1 over x, right? Now, looking at those equations, we can actually define a set of rules to find integration. So that will be our first step. And there is one definition, one such definition for the, if you have a power to integrate a function with some kind of power, then you can use this theorem right here. So that will be the first one. Power rule for integrals. This comes, number one is the power should not be equal to minus 1 for a reason that you will see in a minute. If you have a power x to the power n power, x to the power n dx, to integrate, the answer will be x to the power n plus 1 divided by n plus 1 and then plus c, right? So that constant always comes, right? Now this came by using the theorems that you have learned for the differentiations, right? You just used it. So I got a question that asking whether I'm going to I just have the recording in the classroom. Yes, I will give you the YouTube link to those who could not connect, right? So I understand that some of you have issues with the connections, right? Depending on where you are and what time that you are logging. So if you didn't, if anybody who needs the lecture did not see it within, let's say by Saturday, please post a message for me either in the Google Classroom or in your WhatsApp group, right? So I will I will do that, but in case if you did not see it within next couple of days, just remind me that I will post it then by the end of the weekend, right? So that anybody of you can go back and look at the lecture, right? So this is one equation that you can use to do integrations like you did for the differentiations, right? And you probably can see why I put n equal n should not be equal to -1, because according to this expression right here, if n equal to -1, then -1 plus 1 will be 0. The answer will go to infinity, right? So that should not happen. Now there are a list of tables that you can directly take so that you will see how these functions that you have can be differentiation formulas can be converted to find the integrations. Now, for example, the one of the simplest example is, you know, that if you need to differentiate a constant, the answer will be 0, right? So this is something that you already know. And now, if one way to look at this is, if I need to integrate the constant, then what happens? If you differentiate a constant, the answer is 0, right? So if you integrate a constant, the answer will be kx plus c. So all you need to do is differentiate this function right here, and then see whether you can get this one right here. So that's how you check it. Like that, actually there are set of functions that you can I'm not going to write everything here because there are tables that you can look at these functions. So that's how actually we define the equation above as well. So when you differentiate x to the power n, you get nx into the power -1, right? So what I have done here is for the differentiation of x to the power n, so the dx, so I just look at this answer and do a backward calculation to see how can I obtain the equation, right? So what you did here is put n to the front and then subtract 1 from the n, right? So what I am doing here is I just add 1 to the n, and instead of taking it as a multiplication, I divide it by n plus 1, right? So that's how I obtain it. And by the way, you don't need to you don't necessarily need to know how these things are obtained, but it is always helpful to get the idea, right? Now, this is maybe an easier one. Once you uh, differentiate the exponential, if you remember, the answer will not change, right? So which means if you integrate the exponential, you will again get the same answer, because once you differentiate, you should get this function. And again, when you differentiate this, you should get this, right? So that's how you define it. Right. So you can continue to do this. I will probably post a set of integration functions that probably will be useful for you, but not writing everything here, right? It will take time to write everything here. Now, let me just go for the one example here. That will be right. So when you integrate something, actually you can verify that way whether your answer is correct or not, right? So this is how you do that. So let me just give you two examples. Let's say you have a function something like this, x plus e to the power x dx to integrate, right? So I'm not going to tell you how to integrate this, but I will give you the answer directly. Once you integrate this, your answer will come as x squared over 2 plus e to the power x plus c. Let's say you somehow find the answer for the integration. And now you don't know whether your answer is right or not. All you need to do is take this function and differentiate it. So that will be d over dx x squared over 2 plus e to the power x plus c. So you are going to differentiate this one, right? Now you know how to differentiate it. Differentiate is not that much hard for you now. So you have half here, and then once you differentiate x squared, that will be 2x. And the rules that we learn, when you have this additive sign, you can separately differentiate each term, right? So this is the first term, and then the next term is ex, and we know that e to the power x, when you differentiate it, the answer will not change. So that will be e to the power x. And then the c is a constant, so when you differentiate that, the answer will be 0. Now, if I rearrange these terms, you will get x plus e to the power x. Now, this is what you have here as the integration, right? Now, this explains everything for you. The idea is when you integrate a function and you have an answer at the end, if you differentiate that particular answer, you should get your question back, which means the function that you have to integrate. Right? So that's how you can do this. I mean, that's how you can verify it, right? And one thing the way that I integrate this actually, even though I did not tell you, when I go from here to here, there is an additive sign as you did for the differentiation. From the additive signs, you can do the integration separately. So first I have this function x right here. When you differentiate x, I have used this equation right here. So that means this power is 1. So you add 1, 1 plus 1 is x to the power 2, and then divided by 1 plus 1. This n is right here equal to 1 at this particular situation. So that's how I obtain this one. And then for the ex, once you integrate the function ex, you can see here from this equation right here, it does not change. So ex will be there. And then you have, since this is an indefinite integral, so you have to add this constant c. Right? So that's how you do the integrations, but we will see that there are different methods that you could do these integrations. Now this also tells you that the sum of the integrations you can do separately, right? So you can integrate and then do the summation, right? So just keep that in mind as well. Now a good example that how difficult sometimes to do these integrations is, let's look at. So I will give you this as a question for you. So here is a function x times cosine of x times dx. right? So if I ask you to integrate this, sorry, if I ask you to differentiate this, it is not that much hard, because here is one function x and here is another function x, and this is a multiplication of functions, two functions. And when you have a multiplication of two functions and you have to differentiate, you know how to do that, right? So you just apply the product rule that we learned in the differentiation lessons to this, and you can differentiate it. But it is not like that in this situation when you are going to integrate, right? Now this is why we have to learn different techniques and practice a lot uh, to uh, learn how to integrate different functions. I will directly write you the answer for this integration. That answer is actually x times sine of x and plus cosine of x, right? And then plus some kind of constant, right? I know that you cannot now, for the time being, you cannot even think about how I wrote this answer, right? Because we have not learned any of these techniques for the integration, right? So we have to learn those techniques one by one. And for the time being, let's look at the answer and differentiate the answer and see whether we can verify this, whether x is correct, right? So you have to differentiate this whole function. So that is x times sine x plus cosine of x plus c. Now from the additive signs, you can divide the differentiation, right? So that's we know. So you can differentiate and then add the function. So one function is x times sine x, and then the plus. The next one is d over dx cosine of x, and plus d over dx, the constant. And now this is the product of differentiation. X is one function and the sine x is one function, right? So when you have a function, this kind of function to differentiate, you take this as, let's say, fx, and then you take this function as gx, and then apply the product rule for that particular function. So when you apply the product rule, you keep one function as it is, and then the differentiate the other one. Now here is sine x. Once you differentiate, that will be cosine of x, and then plus you take the other function which you did not differentiate previously, that is x. So the differentiation of x is 1, and then you keep sine x as it is, right? So that is the first part. And then when you differentiate cosine x, you probably know that the answer is minus sine x from the standard rules, and then plus the constant. Once you differentiate a constant, the answer will be 0. Now you can see that the answer is x times cosine x plus sine x minus sine x, right? Now these two will cancel out because they are same. The answer is x cosine x, right? Now you can see it is same as the function that you have to integrate. Right? In this way, you can verify the results. But to verify the results, you need to integrate this and find the answer. So that is sometimes not the easiest one to do. And let me, so I will introduce actually few theorems on the way to the next steps that will help you to integrate different functions. Now, one thing that we saw here is that when you separate, when you have to integrate two functions like this, you can separately integrate them and then add the answers later, right? So let me write that as a rule here. So that is, if you have two functions, let's say fx and gx, and this plus or minus means the two functions may be added together or maybe subtract together, so it does not matter, right? And then if you have to integrate a function like this, the answer will be, you are going to integrate this function separately and you will get an answer, let's say fx, capital Fx, and then you integrate this function and then you will get an answer separately, and then whatever the sign that you have, if it is plus, then it is here, it will be plus as well. If it is minus, that will be minus here, and then plus that constant, right? So in fact, that is what we did here in this question. So you just integrate integrate this function and that function separately and add those integrations together at the end. And the next one is, if you have a constant, let's say you have a constant times some kind of function fx times dx for the differentiation, then you can actually keep the constant out of the integration. You can basically keep the constant as it is and then just differentiate the function simple fx. Your answer will be capital Fx for that, and then plus c. Right? So these are the very basic two theorems that we are learning about the integration. Now using these two, can any of you evaluate this integral, right? So let me take this as an example. So let's say you have to integrate this function. So these type of functions frequently appear in physics as well. Minus 7x squared for times dx, right? Now let's say you need to integrate this function. How would you do that? First thing is, you have to use this rule right here, and that rule, those rules are basically tells you that when you have minus signs, plus signs, and plus signs, you can separately integrate those functions, right? And then there are constants right here, 5 times x to the power 3. So this equation right here tells you that you can keep the constant out and just integrate the function only x to the power 3. And then when you need to integrate a power function like this, x to the power 3, you can directly use this equation right here that we have learned, right? So you are going to basically apply those 3 steps, right? Now as the first step, what you can do is divide each term and you can differentiate separate. So let me do that. So I can separately write 5x to the power 3 times dx, and then minus the next function integrated separately 7 times x to the x squared dx, and plus 3 times x dx plus, and the last function is just a constant, times dx, right? So there are 4 functions separately. Now, when you have a constant like this, you can take that out. So that's what this law tells you. So you take the constant out and keep x squared dx minus, and 7 is taken out, and x squared dx, and plus 3 is taken out, and x times dx plus, and 4, actually there is nothing that you can take out, but you can just take out 4 as well. Now 5 is here. Now you can integrate this x to the power 3. So that will be, look at this equation right here, when n equal to 3, you have to put 3 here and just 3 here for the answer. That will be 3 plus 1 will be 4. So x to the power 4 divided by 4, right? So this integration will be x to the power 4 divided by 4. And then minus 7. This integration right here, basically you add 1 to the power, that is like 2 plus 1, that will be 3, and then divided by the same number. So that's what you are doing here, divided by 3 plus 3. Again for this one right here, x to the power 1 is there, so you add 1. So this will become x squared, and then you divide it by 2, and plus 4 times x, right? So when you have a constant, you just integrate, and your answer will be x. And then, in fact, for each integrate, you will have a constant, but I will add all the constant and put 1 here. So this should be your final answer for the integration, right? And so I'm going to write for the next. I'm going to divide this lecture actually in 2 parts. Now today I will stop from here, and let me take the next one. I hope that it will be okay for you if I take another class on Saturday night or Sunday night. So let me know if you have any issues by taking a class in that way, because rather than just continuing doing this, since we have this opportunity to do it online, I would like to, because the learning integration is not as same as what we did in the differentiation, because differentiation is straightforward. Once you know the rules, you can straight away apply those, right? So I am going to give 3 questions for you. The question 1 will be to integrate x squared plus 4x to the power 1 over 3 divided by x times dx. Now see whether you can integrate this, and let me see this. Yes, I will give you a hint as well. You can probably divide each term by x and write each term separately in this way, and then do some calculation, like just take those as powers and then apply the power rule separately for each term, so that you will get an answer at the end, right? So that's how you can do this. And the next one will be question 2. So you have to integrate 4 over 1 plus x squared dx. Now this one, you have to check the standard integration rules, which I will be posting to the Google Classroom just after the class. And so those will be important for you in future as well. And look at uh, what what is the answer you will get as an antiderivative for 1 over 1 plus x square, right? So if you look at those formulas, you will straight away see that. And the other question is tan x cosine x that you have to integrate. Right? Now, before you integrate this one, and I will give you a hint for this one as well, write the tan x right here as sin x over cos x. Now, for the integrations, if you can first simplify the expression you have as much as possible, sometimes it becomes easier for the integration, right? So simplify the expressions tan x, you can write it as sin x over cos x, and then you can just simplify it, and you will see once you simplify what you would get. And then directly you can apply the one of the formulas that you know, right? So these three questions will be for you to complete, and just check the Google Classroom tonight. So I will post some standard integral formulas, which is also available in the book, but I will copy that page and paste it to the Google Classroom as well. Try these three questions, and please make sure you try these, right? Because if not, you may not be able to learn this yourself. And once you try the three questions, so I will give you probably tomorrow, so that you can try the equations. And of course, these answers are also available in the book as well. So I'm just taking those examples, so you can look at those and understand and try to write the answers, right? But if you don't understand, then don't write it, because then I will once you have the answers. So my assumption is you will know all this stuff, right? Because of that, if you cannot understand what is written in the book, or if you cannot find the answers yourself, then don't try to just copy the answers, right? Because that will not help. So if you cannot understand, just let me know. That if you don't know how to write it, then I can show you the way how to do that.